My name is Uli. I make stuff work. I gave lectures at some YAPCs and Perl conferences in the past, but not in FOSDEM, so if some of you don't know me yet, that's me. In addition to being a software developer, which is why I'm here, and a translator, I also dabble in music and amateur musician. So this Perl computer music thing is one of my personal projects, and I've seen some people make a disclaimer about personal projects that the project does not reflect the views of their employer. Well, I'm self-employed, so I can't disclaim that. However, I can say I don't think there are any controversial views here, which I apologize for. And computer music. Well, computer music is basically not very well defined. One might say any sort of music where a computer is used as part of the performance or composition or anything. The thing is, computers are in everything today, so I wouldn't really say I would call everything computer involved with computer music. I would say if you make something interesting with the computer. And there are a few things you can do, different things. There is MIDI. MIDI is something, most of my examples there will be about MIDI today. And MIDI is used both in real-time performance. It can be recorded in files. MIDI is essentially a protocol for communicating performance events between different devices. And I'll go more into it a bit later. There's sound synthesis. Of course, computers can be used to synthesize sound. This is before computers. And there is software synthesis, there's hardware synthesis. Software synthesis, of course, is a bit newer. Hardware synthesis exists before, but with faster computer, we can do lots of things. Software which used to be done all in hardware. Computing music performance. There are a lot of musicians who use various kinds of computers and software. They use it for performance, they use it for interactive music. Usually it's not fully interactive. Interactive means the computer, whatever the software on the computer interacts, responds in some way to the musician in real time, and it can hear them. Sometimes it's acoustic, sometimes the performer plays into a microphone, and the computer can figure out the pitch tracker what it's playing and respond to it. Sometimes it's using various electronic instruments, MIDI controllers. I've had a very interesting project when I was studying electroacoustics where we used Arduino and the Arduino, the open source board, the open source hardware. And I connected some physical various levers and stuff to the Arduino, and this information, into sensors, and so my physical actions were translated into messages to the software, and the software used that to send controlling messages, some of them MIDI, some of them to other software. I also learned that project that one should read one subject line before one sends email. When I was constructing the project, my instructor said, why don't you go, if you want to build something physical, some tangible instrument, tangible controller, just to go to a flea market, get some junk, find some nice centerpiece and build around it. And after I bought it, I took pictures of stuff I bought, and I sent it to the instructor. And originally, I just sent a subject line, here are photos of my junk. Fortunately, I reread it before I sent it, and I just put a nice subtitle in that. And fully interactive is quite difficult, so usually musicians use lots of triggers, which means there are lots of stuff which is prepared before the performance, and they set up some sort of buttons or some controllers that trigger a specific short piece of music, short trill, short effect. So triggers are somewhat interactive, but they're not full interaction with the computer like another player. It's sort of controlled ahead of, it's small things that are prepared ahead of time and used in performance at the right time. For instance, when I was doing an electroacoustic piece, which is also on YouTube, if you look my name up, you can find it. There are some of the sounds there are prepared and synchronized. Some of them I was triggering during the performance as sort of some improvisation. Controllers are, of course, any kind of instrument that is used to control a sound source. Most controllers are MIDI controllers, and most of these are keyboard instruments, because these are probably the simplest kind of instruments to connect to simulate, to build as an electronic instrument. There are also, of course, MIDI controllers which are not keyboards. There are wind instruments, string instruments, anything people can build. So first I'll talk a bit about MIDI, and before I go into using MIDI, I'll just explain a bit what MIDI is. MIDI doesn't record music, it records performance. And I think the simplest way to explain that is by an analogy of something which is simpler for us to imagine, and that's player pianos. Player pianos, you may have seen them in some old movies. This is the piano that stands at the side and plays by itself, not because it's haunted, but because there's some sort of large roll of paper going through it. And the way it was done, the company that made those player pianos, the most famous one was Pianola, and that name was actually became the generic name for player pianos, like Frigidaire for a Frigidaire, or like Xerox for the photocopy machine. And those machines had recorder pianos, and they would sit a player at the piano, and when he struck a key, it would make an indentation in a paper roll, and the depth of the indentation would be dependent on how hard the player struck the key, and the roll would go on, and the entire performance would be recorded on the roll of paper. And then they would send the roll of paper with lots of copies, send it to other people, and when you ran the roll of paper for a player piano, it would duplicate the performance of the musician. However, because it was a different piano, it had a different sound, possibly different tuning. It might have been completely untuned. So it's recording only the performance and not the sound. MIDI works much the same way. Curiously enough, there are lots of piano rolls in various storage spaces around the world. And George Gershwin recorded about 300 piano rolls, and they still exist somewhere. And there are piano rolls enthusiasts who are very enthusiastic about piano rolls, the way very enthusiastic about Perl, who want to convert them to something we can hear today. And there are two ways of doing that. One way is to get a player piano, spend lots of money fixing it up, getting it to a studio, running the paper roll through it and recording it. Another way is scanning it into a computer using some special scanner and converting it into something like MIDI, for instance. Perl has several, that's actually the next one. Perl has several MIDI models. And just to go through them, I go for a project I've done. And when you start composing, I've done some arrangement and composing. I composed a bit, arranged a bit, like musicians do. So when you start writing a piece, sometimes you start with a motif. A motif is sort of like a short melody, which is probably recurring through the piece. Sometimes it will be precisely duplicated. Often it will be modified a bit. And a number of ways, of course, can be used to record this motif into the computer. I can take a keyboard, a MIDI controller, connect the computer and play it. That's one way, and use a sequencer program to record what I do. However, Perl provides us other ways to do it. For instance, there's a host of MIDI models used in Perl, and one of them is MIDI Simple. MIDI Simple, I would have to say, it stands apart from other MIDI models, and that's not a value judgment. It just simply works completely disconnected from all the other MIDI models. It's its own model. It doesn't have anything to do with the other MIDI models. And in fact, it has a lot of drawbacks. It can only handle one track. First, I'll say something about tracks. Tracks are, this is a term that's coming from old recording technology, where they had this big reel tapes they record on, and they could record on, and the recording had recorded on parts of the tape, and you could record one track, and then the next player could hear the original recording while playing on the next track, and the sounds of the recording would be synchronized and all mixed together. And even though now we record everything in digital, it's a very useful concept. So this terminology holds over from the analog age to the digital age. And MIDI Simple, while it's very limited in some ways, I like it because it sort of creates a very nice DSL, a music DSL, domain-specific language. And if you know a bit of music and a bit of Perl, you can possibly figure it out. And N simply means note. And the second parameter, the first parameter, N is the function parameter, actually. And the first parameter means what length note. And you have here HN for half note, that's 2 beats, and QN, that's a quarter note, that's usually 1 beat in 4/4 music. And we have EN, that's an 8 note. And we don't have 16th notes here, but we do have DHN, which is a dotted H note. That's a dotted half note. That's the dot adds 50% to the length of the noted dots. So this is very, very nice to figure out, very, very simple to figure out. And the second parameter, that's the note itself, and here it uses MIDI terminology for it. The notes are the American style, you use the alphabet to denote the notes, and the number after the note, that's the octave number in MIDI. MIDI gives each octave on the keyboard a number, and G4, that would be the G or Sol on the middle octave, the octave just above the middle C. And you can see the lowercase f there, that's a flat. So this creates this motif which I decided to start my composition. And this may be time to just, I will go back to that. And this is the MIDI file it created. This is the MIDI file it created. And I'm just going to open it with, it's not open here. Opens here. I'm going to open it with this. Now this is a Rose Garden. It's one of the sequencer programs. And once I open it here, actually I should have mirrored it. And I can open an editor. I can open in the default matrix editor. What I actually want to show is the matrix editor. And it's not opening, and we'll just leave it alone for now. Okay, we're just going to leave it alone for now. Let's go back here. Okay, what I wanted to show was that, I didn't show it here, that even modern sequencing programs, they use two different views to show you the notes. One of them is sheet music, which is very convenient for people like me who learned classical music. But some people are also comfortable with reading notes. So the other view is here, in that program it's called matrix view. In some other program it's called piano roll view, which is the analogy I made before, so because of the similarity between MIDI and piano. Okay. Now I can go back to the other MIDI models. And here is just the MIDI models. I want to see what kind of events were written into this MIDI file which I created. And we have the model, well, basically just say use MIDI, and it includes all the other MIDI models except for MIDI simple. And the one I want here is MIDI opus and MIDI track. MIDI track is not seen directly here, but that's what MIDI tracks return. Okay, opus is just a nice word for a piece of artwork, a piece of art, a piece of music. It's not MIDI terminology, it's Perl MIDI terminology. The MIDI terminology is song. Because the people who developed MIDI came from, but they were thinking about pop music. Pop music, one piece of work is a song. But whoever wrote this MIDI model, I have no idea who it is, but I'll buy him a drink if I find out, if I look it up, if I run into him. I just like the word opus better. And what opus does, in this here, it can read, it opens an existing MIDI file. It's very simple to read. Then I read all the tracks into an array, and each track is an object of type MIDI track, which we may see in a later example. And then I just use a loop to loop over all the events and output all the events. And it looks something like this. Note on, note off are the most common events in MIDI, and it's very simple to understand. Note on simply means like you strike a key. If it's a keyboard, you strike the key, and note off, you pick up your finger, you stop holding the key. The four parameters there are delta, channel, note, and velocity. Delta is delta and duration. How much time since the previous event, not necessarily the previous note. So it is actually possible to use this to play several notes simultaneously. If the note on is the delta from the previous note on is 0, it means they're playing at the same time. Here I don't have two notes playing at the same time. The delta 0 is from the last note off event. The number is duration in some internal counter. Channel, that is a logical channel. You can play MIDI several channels. For instance, you want to play several different instrument sounds at once. You can say channel 1 is going to be piano sound, channel 2 is going to be trumpet sound, and then everything is sent to channel 1 afterwards, plays with the piano sound, everything is sent to channel 2 afterwards, plays with the trumpet sound. Channel 10 is usually reserved for percussion. The third one is the note number. Before we saw the note names like the G5, C4 and everything, which is just very convenient for humans to look at, but every note also has a number. So G5, the note number happens to be 55, and the note after that, the number is 60, and the numbers follow. You can just count from on the keyboard. If you follow all the notes, there are consecutive numbers on the keyboard. The last one is velocity. Now, in normal English, velocity seems simply another word for speed. In MIDI, velocity is another word for volume, which sort of makes sense if you know how a keyboard works. And when you want to play loud music on the piano, you hit it harder. What actually happens, and there's an entire mechanism there that you hit the key and it lifts the hammer strikes the string. But what you really get is a lot of kinetic energy, so when you play louder, the key actually goes in faster. So this really comes from the engineers who devised the way to figure out how to play loud and soft on an electronic keyboard. Because if you go back 30 years to the 80s, if you bought a keyboard back then, those keyboards could only play with a single volume. They were not touch sensitive at all. So it was a huge drawback. So the engineers tried to figure out how to be touch sensitive. They tried to measure a few things, and they discovered that if the key goes in faster, it means you're playing louder. So velocity in MIDI actually means volume of a specific note. Okay, what I wanted to do with this motif, what you usually do when you start composing music, and the motif is supposed to recur throughout the piece. Now, the simplest way, of course, is to repeat it exactly the same way. But that's not very interesting. It's more interesting to develop it, to make slight changes to it. And normally I would sit at the piano keyboard or the MIDI controller keyboard and try to play a bit with it and play the motif, try different versions of the motif, try playing it maybe a bit faster, slower, change a few notes. If it's a minor key, try to play it in a major key. But then I thought, is there a way I could use some sort of algorithm to explore the melody space? Maybe there's an algorithm that can suggest to me other versions of this motif that I would like, that would be pleasant for me to hear, that would be interesting for me to include in my piece. And I thought, what sort of algorithm would give me approximate solutions, approximate answers to this question? So I turned to an algorithm I used before successfully. Because I said now, okay. Question to put, what is similar? What does similar mean? Similar, of course, sounds the same melody, sounds the same rhythmic pattern. And in this particular case, I was actually looking for something where rhythmic pattern was more important to me than the melody. And the algorithm I figured I could use were genetic algorithms. Genetic algorithms are algorithms that use the concept of evolution to arrive at a solution. They don't guarantee a solution. However, they're very good at quickly arriving at approximate solutions. And a couple of years ago, I presented a way that I used genetic algorithms to synthesize sound. And in that case, I wanted a very precise solution, which I was close to arriving at. Here, I wanted a very imprecise solution. So what I tried was a somewhat unorthodox use of genetic algorithms. And I figured if I use them improperly, I could probably get some nice suggestions for variant motifs. So first, my very, very brief primer about genetic algorithms. For genetic algorithms to work, first you have to find a way to represent the problem. You need to take all your parameters, all the problem parameters, figure out what they are. They could be numbers, they could be strings, they could be range of numbers, they could be switches, whatever, and write them out. You just write them out as one log list of parameters. You have genetic operators, you have a fitness function. Genetic operators are, okay, well, let's start with the fitness function. The way you work with genetic algorithms is you start with a random population. The first population you create are completely random solutions. But of course, they're not good solutions. Then you run your fitness function on all of them. You rate them, you give them each a grade, and these grades about how well they solve the problem, they determine which solutions get to breed and create descendants for the next generation. Not only which ones, but how many descendants they get to have. Genetic operators are things like crossover. I mean, how do you take two solutions and mix them up? And usually you just take a few parameters from the first one, a few from the second one, and you mix up the parameters, and you get a new solution which has some characteristics of the first parent and some characteristics of the second parent. Other genetic operators are random mutation, which you don't want to have too much of, but it's good to have. And so my first thing, before I could start doing genetic algorithms, I needed to create a representation of the MIDI melody. Now, one property of melodies when you use the Western keys and Western tonal system is if you transpose a melody by several keys or several notes up or down, it sounds the same. So I don't really care about the first note. It's the same note for all of them. And what I do care about is the durations, because if I have to compare the durations, I have a rhythmic pattern. How the rhythmic pattern is. I care about the intervals between the notes. If a melody starts with a note going from G to A, that's one tone up, 2 keys up. I want to record that. Another thing was, I figured I can handle strings pretty well, and things like string similarity. So I decided to encode the melody as a string, where the first character is the duration. Well, the very first note is fixed, so I don't care about it. So the first character of the string is the duration of the first note, because that is a parameter that may be changed. The second is the second note, and the third parameter after that is the duration of the second note, and so on until the end of the string. And just to make things simpler, I just used uppercase characters for descending intervals and ascending intervals, and lowercase characters for descending intervals. For durations, I said, well, I'm just going to divide everything into 16th notes. So a quarter note would be 4, and a half note would be 8. And use the characters from A to H, from A to the first 16 letters to denote how many 16 notes they have. And the longest note I can have is a whole note. So I also limited myself in how long the notes can be. So this code, it just takes the same thing we saw before to create the list of notes, and it creates the chromosome this way. The chromosome, that's the terminology used in genetic algorithms. We use a lot of terminology from genetics. And this would be my melody encoded as a chromosome for the purpose of the fitness function. For the genetic algorithm itself, I used another model I've used before successfully called AI Genetic Pro. It's quite fast, it's got very good performance. It can handle lots of very large populations. Oops, I'm doing a time list, not of well. Okay, and when you start doing a genetic algorithm with AI Genetic Pro, there are several things you need to give it. First, reference to the fitness function, because you need to write your own. You need to write your own because the fitness function is specific to the problem you're trying to solve. The rest of the parameters are pretty straightforward. Type, list, vector, this is what the kind of the kind of what type of chromosome. If I give a list of parameters, it's a list vector. If I just want to give a list of ones and zeros, I can tell it's a binary chromosome. There are other options. Population, 1,000 is a very big, nice number for population. If populations are too small, you don't have enough genetic diversity in the population, and you might reach, you might get an early divergence on a very bad solution. So population needs to be large. Crossover, this is the chance of a crossover. What is the probability that crossover will happen when two solutions mate? Mutation, this is also a probability. It should be a very low one. If it's 0, then you might miss out on some very good genetic possibilities, which are not in the population right now. If it's too high, it might actually spoil some good advances that you've made so far. So it should be low. Usually 1%, 2% is 0.1, 0.2 is all you have. Parents. Unlike biology, you can select the number of parents. 2 is fine. Sometimes you can have also 3 parents for one solution. Selection. Selection is how the selection is being made. How are the parents for the next generation are selected? And there are all sorts of different strategies. I'm not getting into them now because that's not the main thrust of the talk. This is one of them, roulette distribution. There are also others, there's roulette. And basically it says that instead of determining ahead of time how many descendants each solution will have according to its rating, it determines the probability of whether or not it will have more descendants. It comes about the same point. Strategy points to, this is strategy of how the crossover is made. This is a 2-point crossover. The difference between 1-point crossover, 2-point crossover, 1-point crossover, only 1 point is selected on the chromosome, and then everything before that point is switched between the 2 chromosomes, and it's created the new generation. A 2-point crossover, 2 points are created, and then everything between them is switched between the 2 chromosomes, and that creates the new descendant. So everything from the first position to the first crossing point comes from parent 1. Everything from the second crossing point to the first crossing point, second one comes from parent 2. Everything from the second point to the end comes from parent 1 again. Again, what is better? This is a lot of trial and error. Except in this particular situation, I was not concerned, thank you, with precision. In fact, I wanted imprecision. So this was how I started my initialization. This is how I tell the genetic algorithm model what to put in the various parameters. As you can see, I have my duration parameter is the first one, and the second one is my interval parameter. My duration parameter is, of course, 1 to the first 16 letters. My interval parameters is lowercase letter, uppercase letters presenting descending and ascending intervals, and 0 is presenting the same note. Okay. And then when I want to start telling it to evolve, there's the method evolve. The number in parentheses says how many generations. The more generations you have, the longer it takes, and the better results you get. Usually everything under 30, 40 is pretty useless, but get fittest gets me the n, in this case 40 top candidates, the one who got the highest ratings, and the last one just to print them out to a file, because I want just to keep the chromosomes themselves, to keep a record of them. The fitness function, this is really the heart of the matter here. It represents all the things I care about. Well, not all of them, because I cut it halfway, but represents the things I care about when I want to mutate, what I consider to be similar. So I have the descriptions, which I created yes, I created them as another function. Descriptions of the 2 melodies, of the original melody and the candidate melody. And one description, I break it up before I do this into intervals and durations. Durations, I get the rhythmic patterns. From the intervals, I get the melody, whether it's going up, down, sideways, whatever. And I compare them. And I have the intervals with the melody. I have the inverted melody, which is exactly, inverted melody is exactly the opposite of my melody. If my melody goes da-da-dum, the inverted melody goes da-da-dum. It's exactly the opposite. It's useful. Inverted melodies are used a lot in fugues, more than in other types of music. And I'm saying if it's similar to inverted melody, it could also be a very nice variant motif for me to use, but it gets a lower score than similarity to melody itself. Durations, similar to durations, also get it. And I'm not sure it made it in here. Oh, yes, actually it did. Maybe next time. To check similarity between strings, I just use a combination of models that do this. LCSS, the largest common substring, which is nice but not good enough for the particular. Yes, not quite good enough here because a string might be modified in the middle, but the bigger substring is still quite similar. So I also use trigrams and something called string similarity. Trigrams are very useful to find similarity between text. They're used in translation memory when you need to find a similar sentence to the one you have now. The entire text is broken up into sequences of 3 characters. It's not from 1 to 3, 4, 5, 6. It's 1 to the first, second, third, and the second, third, fourth, etc. And then they're counted. And if the count is similar between 2 texts, then the texts are probably similar. In fact, if you take a text in certain language and you create trigrams, then you create a random text from those trigrams, someone who does not know the language might think it's that original language. It looks that similar. And string similarity is another model which uses another algorithm for similarity. And okay, we have 5 minutes. And any questions? Just quick questions about this. Yes, please.
Would you please demo some? Yeah, I really want to hear it.
Yes, I want to hear it too, but unfortunately I don't have sound here. So it will be on my site. It will be on my website, all of this. There already is one posting about whether my site without sound. And I was playing it, yes. And my site, it's Brook.co.il, bruck.co.il. So there's one where the poster without sound, and I'll add the demos there. And I'll add the stuff about synthesis, which I didn't even get to also. And probably there within a couple of weeks, 2 to 52 weeks at the most, that's usual stuff. Any other questions except for demos, which I... Yes, please.
Yeah, I have one question concerning Perl applications in general are single-threaded. Say I want to do something with MIDI music or make music, or for
Yes.
example, I want people from the internet to be able to make music on my machine for whatever reason. But that would mean I would have to make music and do other stuff at the same time. Would it have any impact on the responsiveness or the delay in all the MIDI handling?
It probably would, but if you do that, I probably wouldn't use Perl for that.
So, would it be really noticeable, or would everything be fast enough to just not care at all?
Sorry?
As in, can I do MIDI handling
Yeah.
and do other stuff at the same time?
Well, first of all, you probably do it all the time, because your phone can play MIDI and your computer can play MIDI files, and they do it all the time.
Okay.
So, yeah.
That's good.
Yeah. Okay. Any other questions, if I have time? Thank you.